One of the most difficult things for students to do is to take what they have learned in class and transfer it into the real world. In this particular laboratory, you have a tube, and coming up through that tube is a string. At the end of that string is a mass that we'll call M1. In the laboratory, you then swing the mass in an arc and measure the radius of that arc. If you were pinching the string and holding it right here, you would know that the centripetal force is the mass of that object times v squared over r, where r is the radius of this orbit. V squared is the square of the velocity, the tangential velocity. How do you calculate this? Well, you have a partner, calculate maybe 10 turns. And in this 10 turns, you calculate the amount of time that's gone by. So let's say t is the amount of time that's gone by. If you had 20 turns, the total distance that the mass has traveled is 20 times 2 pi r. R being the radius of this circle that you're swinging it in. So you take the 20 times, the time that you did for the 20 times, divide that and multiply by 2 pi r, and you get the tangential velocity. That gets squared and put into this equation. Now consider the other end of the string as if it were by itself. Let's say you tied the string right here that comes up through here, but let's say you tied it here. At the end of this is mass 2. With what force does mass 2 pull down? Mass 2 pulls down with a force equal to mass 2 times acceleration due to gravity. If I lift the entire thing up, I have to apply an additional force. If I pull it down, I have to apply an additional force. If I simply hold it here with no movement at all, then the force I exert by holding it is this second mass times acceleration due to gravity. Now let's put the two problems together. Here we have a string. Let's put it right in the middle. Tied down this way, I have M2 pulling with a strength of force equal to M2 times G. This is a gravitational force. Coming out this end, I have the mass M1 swinging around, and the tangential force holding this in is equal to M1 times V squared over R. That gravitational force, if it's counterbalanced exactly, and we'll paint this little piece of the string white and make sure it doesn't move up or down, then the gravitational force must be exactly balanced out by the tangential force. So the gravitational force is M2 times G. Therefore, the tangential force must be equal to the gravitational force, and we have M1 V squared over R is equal to M2 G. G is, of course, the gravitational constant, 9.8 meters per second squared. M2 we measure in the lab. M1 we measure on the balance in the lab. V squared and R we calculate by taking a meter stick and measuring the length of the string we have at the top here. And we measure the velocity by what we just spoke about, where we take 2 pi r, the number of turns, divided by the actual time that took. What we are trying to determine in the lab is, are these two things equal to each other? They should be, but the amount by which they are different is going to tell us the percent uncertainty, sometimes called the percent error in our measurements. And it actually is an error here because we know they should be the same. So, to calculate the percent error or the percent uncertainty, in this case it's really an error in our measurements, we take the one minus the other, mv squared over r minus m2g, absolute value of that, whatever that difference is, and then we don't really know what truth is because both these were actually measured. V squared was measured M2G is actually the more accurate measurement here. And so I would think we divide this by M2G, because we can easily measure the balance of M2 in the lab and G, and that is the most reliable error there. We multiply that by 100 and we get the percent error.